And hello there, and in this video we will go through reduction of order, the method that's being presented in the textbook, through a simple example. So let's go there. So the example I chose to go through is the simple constant coefficient homogeneous second order equation. As you see, it's y double prime plus 4y prime plus 4y equals to 0. So I chose some nice numbers. As you see, if we write out the characteristic equation, I have a perfect square. R1 equals to R2, which is -2, so I have repeated roots. Okay, so the difference between this example and the textbook one is A equals to 2 in this specific example. So, we can find one solution, which is y1 equals to e to the -2t. Now we want to find the second solution, y2. Now the whole point here in this method of reduction of order is that, assuming that we do not have a powerful theorem such as Albert theorem, just the equation and the information of one solution, shall we be able to find the second one? Okay, so the method goes as follows. So we will be guessing a solution of the form, that is, the second solution shall equal to the first one multiplied by a function v of t. Now the goal will be, I need to find this vt without using our theorem. Okay, pretend we don't have it. Okay, so what do? Well, you would plug in y2 back into the original equation right here. So to prepare ourselves ready for this process, I would write out. So now what is my y2? y2 is v times y1. y1 is this exponential function, e to the 2t, which I plug here. So I see I need the derivatives, so I prepare myself. So the y2 prime, I will use product rule on this expression and work it out. So it will be v prime times the exponential function plus v times the derivative of the exponential function, which get a -2 in the front. And then we see that e to the -2t is a common factor. Let's take it out, and what remains here will be the v prime goes over here, right? And the -2v goes over here. Okay, so if during any part of this video you think I'm going through too fast, you can pause and look at the formula to slow me down. Okay, and then we have y prime, and I need to differentiate it one more time. And again, this is just an application of the product rule. So I will be differentiating e, keeping that, and then keep the exponential and differentiate that. So you can carry out that computation on your own, and after I collect e to the -2t as a common factor, move it out, and this is what we will have. Okay, so now we are ready to plug these three expressions into the equation and set it in, and let's see what we get. Okay, so we plug it in. So the equation here will be, this is y double prime plus 4 times y prime plus 4 times y equal to 0. First, we observe that e to the -2t, this is a common factor everywhere, so we get rid of it. Okay, and let's see what we have. Okay, after we got rid of it, now we have that term left, and then I multiply the 4 inside, and I get this term, and then I have a 4v equals to 0. Now let's see. Some cancellation is still happening here. We see this is -4v prime, and this is positive 4v prime, so these two would cancel, right? And look at the terms involving v. I get a 4, and I get a -8, and I get another 4. If I add the numbers up, 4 minus 8 plus 4, it's 0. So this term is gone, and this term is gone, and this term is gone. Now pay attention. This has to happen, okay? It's not coincident that it happens for this example. It will happen for all the example if you carry out this procedure. Okay. So what are we having in the end? We have only one term, which is v double prime equals to 0, which we can easily solve. So what functions the double derivative is 0? Well, it has to be a linear polynomial, right? Nothing else. You can integrate it twice, and you will get that v of t. Okay, then plug back. We know the second solution. y2 now is v times y1, which is this v here. That's the function now consists of two arbitrary constants times y1. So if I distribute it, I'll get c1 times this and c2 times that. So now pay attention. This guy here, e to the negative 2t, this is just y1, and it's multiplied by an arbitrary constant, right? So we don't have to take it with us in the general solution, because we're going to multiply it by arbitrary constant anyway. So this term we can remove. And then for the first term here, we know y2 will be multiplied by an arbitrary constant. So adding a c1 there doesn't really make a difference. So what can we do? Well, we can just take c2 to be 0, so this term will be gone, and we take c1 to be 1, so this will be 1, and that will be the simple expression for y2, which is t times e to the negative 2t, or which is of course the same as the y2 we obtained in class using the fast method number 3. Okay. So as you see now, this method here does require quite a bit of calculation, doesn't it? It requires you to find all the derivatives for this y2 prime, y2 double prime. You need to figure them out, and you need to plug in, and you need to find the cancellations. And then you still get a second order equation, even though you will be able to solve it. Okay. So this is actually a very simple example with constant coefficient. If your problem shall be not constant coefficient, meaning coefficients are now functions of t, it will be even more complicated, though it always works out. So maybe I'll make another video on that, but we'll see. Okay, some comments on this method. So it's a more complicated method in computation than our fast method number 3, well, not the first, the third method. But however, notice that this is a more general method. You have to agree. It's more general because it does not require Abel theorem, right? Abel theorem is very powerful. In case you don't have Abel theorem, by this method, you can always carry out and reduce the order of the equation by 1 and figure out the second solution. Okay. So let's make some connection here. So a similar situation also occurs in finding roots of polynomial, if we recall what we learned when we were finding roots of polynomial. So say you have a polynomial, let's call it Pn of t. It's a polynomial of degree n, so it should have, in principle, n roots. You know, in general, it's not so easy to find these roots. And then, in case, by some chance we are lucky, we found one of them, R1. Then we know the polynomial must have a factor t minus R1, right? Which means you can write your polynomial as t minus R1 times another polynomial, q here. What happens to this q? Well, this q is a polynomial of degree 1 less compared to that of the original polynomial you started with. So by knowing one root, you could reduce the degree of the polynomial by 1 and find the rest. So, hope this is helpful. As always, let me know if you have any comments. Okay, bye.